Good morning, good afternoon, good evening, wherever you are. Welcome to this week's edition of HoloTube, and we are very happy to have Xu-Guang Huang from Fudan in Shanghai today, talking about the recent developments in spin hydrodynamics, inclusion of spin into hydrodynamics, necessitated by some experimental data, and we are very excited to hear some about data, especially. So, oh well, like whatever you like to tell us, Shugang. So the floor is yours. Thank you.
Yeah, thank you. First, I thank the organizers, especially Matthias, for the invitation. I'm very happy to give a talk for this HoloTube online seminar series. I'm going to talk about the spin hydrodynamics and the Lambda polarization in hadron collisions. This is not about holography, but I think, or I hope that you will find that the topic, the spin hydrodynamics, even more general, the spin transport phenomena in the strongly interacting matter, the QCD matter, or even the rotating QCD matter itself could be a very interesting playground for the holography. And all the holography may provide some new interesting or special perspectives to this topic. Okay. Yeah, so I will follow the suggestion from the organizers that first I will give an introduction to the spin polarization phenomena in hadron collisions. Basically, the lambda polarization in hadron collisions and its current experimental status, and also the theoretical understanding so far. From this half of my talk, I hope you will agree that the current understanding to the lambda polarization phenomena is not complete. So I think it's quite important to have a theoretical framework in which the spin degrees freedom is treated as a dynamic variable. And with that, I will turn to the spin hydrodynamics. That is the hydrodynamic framework for the spin transport. Finally, if the time permits, I will also talk about our recent work about the calculation in the perturbative regime for the spin relaxation rate of heavy quarks in a hot QCD plasma. So finally, there will be a summary and outlook. So okay, so I'm not sure whether the audience are familiar with the hadron collision. So let me start with some very basic facts about hadron collision and quark-gluon plasma. So now there are two major colliders in which the hadron program can be operated. One is the relativistic hadron collider in US, and another is the Large Hadron Collider in Europe. So in these colliders, the heavy ions like the gold nuclei and lead nuclei can be accelerated to a very high energy, and then they collide. So in such a way, the quark-gluon plasma, that is a deconfined quark-gluon matter, can be produced and studied by measuring the final hadronic observables. Okay, so from those hadronic observables, we could extract some properties of the quark-gluon plasma. That's the way how can we study the properties of the quark-gluon plasma. Of course, the studying of the quark-gluon plasma is very important and of course interesting, and it's also occupy an important portion of the QCD phase diagram, right? So the quark-gluon matter could appear at high enough temperature or high enough density. So those measurement that can be used to study some properties of the quark-gluon plasmas are the probes of the quark-gluon plasmas. So usually those probes are based on the charge or flavor property of the hadrons. So here is one of the examples. We can consider the charged hadron spectrum as a function of the azimuthal angle phi. So here, as a function, the spectrum as a function phi, and usually this function is not it's not a homogeneous function of phi. So we can do the Fourier transformation to study different Fourier components, and the first component is the directed flow with the Fourier coefficient called the directed flow coefficient. And the second one is the elliptic flow, V2. So those quantities, those Fourier coefficient can be measured at a very high accuracy. For example, here I show you the data from the atlas at LHC. So this V2 and also V3 and so on can be measured to a high accuracy. And from this measurement, what we can know about the quark-gluon plasma is that there must be some anisotropy in the spatial distribution of energy in the quark-gluon plasma. And if the data is enough, we can also extract some other properties of the quark-gluon plasma, like the transport coefficient, shear viscosity, bond viscosity, and so on. And we know that those transport coefficients are depending on the dynamics of the quark and gluon. So this way we could study the properties of the dynamic properties of the quark-gluon plasma. So then we can call those probes that are based on the charge or the flavor. So flavor, I mean, we can also look at, for example, proton or charged pion or electron and so on. Yeah, all those observables we can call the because they probe some specific transport in the quark-gluon plasma, like how the charges are transported in the quark-gluon plasma. So this is like the electronics, or maybe it can be called the flavortronics of the quark-gluon plasma. So with this, we can compare this to what happened in solid state physics. So in solid state physics, first we know that we have this electronics. We know this for almost 200 years, and our modern daily life is largely based on the development of electronics. But in the past several decades, roughly 30 years or 40 years, there is also a rapidly emerging branch of the conventional matter physics, that's the spintronics. So in this field, it's not, in addition to the charge, the spin degrees freedom can be used to develop some special devices like the hard disk, reading head, or some memory devices. Those devices are based on the transport of spin and based on the spin polarization. So that's the spintronics. So which is very interesting and important in solid state physics. And then we could ask whether this is also possible for our heavy-ion collision studies. So could we have also the spintronics for the quark-gluon plasma? So if, namely, could we use spin, or could we detect the spin transport within the quark-gluon plasma? So if this is possible only when we can detect some spin polarization of hadrons, like the hyperons, and then with those measurements we can extract. So we can measure, for example, if we can measure the total spin polarization here, the P, and then how the spin polarization is distributed to different kinematic region, like to different azimuthal angle, then this would be similar to the harmonic flow, the transport coefficient V1 and V2 for the charges. In this case, we could have the Fourier coefficient for the spin. So here I write it as F2, G2, and so on. So from those measurements, we could just like what we have for the V2, V1, V2 for the charges. We could extract the properties of how charges, particles are transported in the quark plasma. And with this measurement, we want to extract, what we want to extract is how the spin within the quark plasma is polarized, or is transported. So in this way, we could say that we could study the spintronics of quark plasma in the heavy collision. And this is indeed the case. About 5 years ago, the first measurement of the spin polarization of the lambda hyperon was successfully done by star collaboration at RIG. So here is the experimental result. So they measure the spin polarization. So here is the definition of the spin polarization. So you can choose a direction. So here the direction is chosen to be perpendicular to the reaction plan. So why this direction is special? That's because this is the direction of the global angular momentum of the colliding system. Okay, so once this direction is chosen, then we can measure the number of lambda hyperons with spin along this direction and with spin opposite to this direction. Okay. Yeah, because spin is you can quantize spin according to any direction, but now if you choose this direction to quantize the spin, then you can ask how many lambdas are with spin up and how many are with spin down. Then you have this quantity, and that this is what is shown in this plot. Okay. So then why lambda hyperon? That's because lambda hyperon decays through weighted interaction, and in its rest frame, its total proton momentum direction is roughly its spin direction. So which gives us a way to measure the spin polarization of lambda. So for example, for proton, although there are more numbers, there are more protons than lambda, but the spin polarization of proton is not easy to measure. So okay, so recently there are also the measurement of cascade minus and omega minus at star collaboration. That's the result appeared last year. And also the Hedis collaboration at GSI also reported the measurement of lambda polarization at very low energy. So with all those results collected, so you see that the lambda polarization, or maybe similarly for cascade and omega polarization, decreases with increasing collision energy. This is somehow anti-intuitive because with higher colliding energy, we expect there would be higher global angular momentum. And why lambda is polarized is because the angular momentum is conserved. So after the collision, some part of the global angular momentum will be transferred to the produced particle. But with higher and higher energy, we should have higher and higher global angular momentum. But why the measured lambda polarization is smaller and smaller at higher colliding energy? That's because what can be measured is only those lambda at mid rapidity, and at the mid rapidity, as I will show that the local rotating frequency, that is the vorticity, is decreasing with increasing energy.
Hey, Xu-Guang.
Yes.
Sorry. Hi. Yeah. Hi. Yeah. I have a question. It's just a very simple thing.
Sure.
So just when you have this, the decay channel, lambda going to p, the proton and the pi plus, and then in the table below, is it one of them is lambda bar, or like is it why this pi minus and pi plus? There's kind of like inconsistent.
You mean here?
Yeah, there, and the one just below the figure up.
Right. This is for lambda. For lambda bar, yeah, there is also for lambda bar.
Right. No. I'm saying like just above that one, and the one above the no, not on the table, but just like this. Yeah, exactly there. That's pi plus, and the other is pi minus. Is one of them lambda bar?
This is not correct. It should be pi
Oh,
minus.
it's a typo.
Yeah, thank you.
Okay. Yeah. I was just confused. Okay, fine. Yeah, thanks.
Thank you. This
So,
should be pi minus.
right, yeah. So this, and lambda is yeah. So if it should decay proton and pi minus. So it's a chargeless.
Right. Lambda is neutral. So lambda bar is also neutral.
Yeah. So how should I understand the difference in between lambda and lambda bar that is essentially coming from the magnetic field when?
You mean the difference in the polarization?
Right. Exactly.
I think so far there's no clear understanding. One possibility is the magnetic field.
But then it's a chargeless particle, so I would expect, if it were charged, I understand definitely that would flip the spins in opposite directions. But...
okay, yeah. But lambda, the magnetic moment of lambda and anti-lambda are different.
Okay, perfect. Yeah.
Yeah, because the magnetic moment of lambda is actually here. It shows this quality. It's largely determined by S quark only. So, yeah, for lambda and the lambda bar, they have very different magnetic moment.
I see. Yeah, but there's no hydrodynamic understanding of the difference.
Hydrodynamic.
I mean, like, magnetohydrodynamics. So can I was just wondering if anybody has reproduced the difference between lambda and lambda bar using magnetohydro.
No, because first, if you look at this data, you can see that there is a big error bar. So within the error bar, actually, we cannot see that there is a clear separation between the polarization of lambda and the lambda bar. They are within the error bar.
Right.
Second, even if we so we say this is the lambda, this is the lambda bar polarization. They are different. As far as I know, there is no hydrodynamic calculation, but there are some models studied based on the magnetic field. Yes, if you tilt, for example, the lifetime of the magnetic field, the strength of the magnetic field, you can produce some of the results. And also, there are some other interpretation for the difference between lambda and lambda bar. One is that with lower and lower energy, you have a larger and larger baryon chemical potential. So lambda and the lambda bar will behave differently at the finite chemical potential. And also lambda and the lambda bar would produce different regime in the collision. Thus, they could feel different strength of vorticity. This could also be possible interpretation of the difference between lambda and lambda. So yeah, there are several different studies, several in the literature. So yeah. I think in future, if the right.
Yeah, I got it. Thanks.
In future, with the beam and scan 2, there will be much more data. If finally the error bar can be suppressed to so that we can see a clear separation, I think this would be very useful to constrain some model.
And are there any plans to study polarization at LHC, for example? I mean, do you know? Are you aware of any?
For LHC, for the global polarization, because they decrease with increased energy, so at LHC energy they are almost zero. But one can study the local polarization. So namely how the polarization, although totally is zero, but they can be distributed to different momentum regime, different kinematic regime. So this can be studied at LHC. And I think Alice has already some result.
I see. So the polarization is a function of the angle. You mean the azimuthal angle? Yeah.
Right. Yeah. Also, the polarization possible. Also, polarization as a function for PT and
On PT, yeah,
rapidity
and rapidity. Yeah. Okay. Cool.
Right.
Yeah. Thanks.
So okay. So that's the global polarization, and which for which we expect that is due to the global angular momentum of the system. But there is also a local polarization. So namely, we ask how the polarization is distributed to different azimuthal angle phi, PT, and rapidity. And for a given azimuthal angle phi or given PT, we can count the same quantity as before, then define the differential polarization. Sometimes this differential polarization is called local spin polarization. Okay. So for example, here is the result from star collaboration for the lambda polarization as a function of the azimuthal angle phi. So you see that when we switch phi from 0 to pi half, so namely from the in-plane direction to the out-of-plane direction, the polarization becomes smaller and smaller. So similarly, we can also look at the longitudinal polarization, namely we quantize the spin to the longitudinal direction. Longitudinal direction is the beam direction, and then see how the spin polarization is distributed to different azimuthal angle. So here is the result from star, and the same quantity is also measured by Alice. So they are basically the same. Even the strength is similar. So so firstly, that's a positive polarization. That's and then there's a negative if you go from 0 to pi. So from 0 to pi half, the polarization is positive, and from the pi half to pi, the polarization is negative. And then if you look at the different harmonic coefficient, the Fourier coefficient, then you'll see that the experiment data gives F2. Z means the longitudinal polarization is positive, and G2, Y means the transverse polarization. Okay, so this is what the experiment tells us. Then, yeah, of course, we need to ask what is proved by the spin polarization observable. Quite naturally, we would expect that the spin polarization probes the vertical structure of the gluon plasma. So that's just because if you have a rotating fluid, there will appear this spin and rotation coupling, and with this, a simple argument can tell us that the spin is polarized in the rotating direction, and the polarization strength is proportional to the rotation divided by the temperature. So which means if we have the polarization, what we equivalently, what we have is angular momentum stored at somewhere in the gluon plasma. For example, the global spin polarization is a kind of measure of the global angular momentum. And indeed, if you consider a non-central collision, you can realize that there is a large global angular momentum. That's the J0. So yeah, which is about 10 to the 6, 1 million H bar. So 1 million H bar is a small number, but it's also a very big number if we compare this angular momentum to the single particle spin, because single particle spin just H bar. So this is the angular momentum. So and after the collision, this angular momentum should be part of this angular momentum should be kept by the gluon plasma. So here, this the angular momentum is equal to the vorticity times the momentum inertia integrated over the full volume that the gluon plasma occupies, which is the vorticity given by this relation. Yeah, from here, yeah, basically this tells us how to calculate the vorticity. And yeah, the calculation can be done by using different models like the transport model or hydrodynamic model. So here I show our result by using Hygiene model at high energy and the QMB model at low energy. Then you can see that just like what happened for the global spin polarization, with increasing energy, the vorticity itself decreases. The reason is that with increasing energy at mid rapidity, the matter becomes more and more transparent. So they are more and more longitudinal, both invariant in the longitudinal direction, and that so that they support lower and lower vorticity. That's why the vorticity at mid rapidity decreases. This is in perfect agreement with the measurement of global polarization. But when the energy is very low, the vorticity increases simply because in this case there is no relativistic both invariance, and the vorticity simply increases with increasing angular. So the vorticity in heavier collision is actually very huge compared to the vorticity in other systems. So that's why sometimes we call the heavier collisions produce the most vertical fluid, because they have the most they have the strongest vorticity. Okay. But the global angular momentum is not the only source for the vorticity. There are other sources for the vorticity. For example, the inhomogeneous expansion of the system. So after the collision, the gluon plasma will expand and cool down. And during this procedure, there will appear some special type of vorticity. For example, there would be this smoke loop type vorticity in the rapid, in the forward rapid region, and also in the backward rapid region. So this is also seen by some numerical simulation. And similarly, if you have a non-central collision, then you can realize that the transverse expansion of the system is also inhomogeneous, such a way that you would have this quadruple type of vorticity. And this is also seen from the numerical simulation. And this quadruple type is very much like what is measured from the experiment for the longitudinal polarization. Thus, it seems quite natural that this longitudinal polarization of the lambda is probably due to the due to this transverse expansion of the media, which induces a longitudinal quadruple structure for the vorticity. Okay, so those are some qualitative picture with this vorticity and with the measurement. We want to build some solid bridge that can connect the data to the vertical structure of the gluon plasma. So let's see how can we do this. So we can consider a local Gibbs state for spin 1/2 fermion for direct fermions, and yeah, this local Gibbs state is given by this density operator. So in which this theta mu nu is the stress tensor, beta nu is the thermal flow vector. So the velocity divided by temperature. And this capital sigma mu rho mu nu sigma is the spin tensor, and the mu rho sigma is the corresponding spin potential, or sometimes called spin chemical potential for the spin tensor. So this is obtained by maximizing the entropy. So under the local caution that locally the energy, the stress tensor and the spin tensor are fixed. Okay, then you obtain this density operator. So once we have this density operator in principle, we could calculate observables in this local Gibbs state. But because the spin polarization is measured in the momentum space, so we want some formula that can connect the spin polarization in momentum space to the distribution of velocity and the distribution of spin chemical potential in the coordinate space. So for this purpose, it's quite convenient to consider the Wegener function, so which is the diffusion function in the phase space defined in this line. And with this, it's quite straightforward to calculate the spin vector as mu by using the Wegener function. So it's a trace of the spin. This is the spin spin operator. This is the Wegener function. So here I use the canonical stress tensor and a canonical spin. In this way, the spin vector is given by this formula, and the spin tensor is totally anti-symmetric. Actually, you can choose different types of stress tensor and different types of spin tensor. So in principle, if you different choice of those quantities could give you different result for the spin vector. That is called the pseudo gauge ambiguity. So namely, what is measured is actually a pseudo gauge dependent. Yeah, I will come back to this later. So anyway, so here we use the canonical spin vector. And then after some calculation, you can find that the spin vector in the phase space is given by this formula. So it shows that the spin potential mu alpha beta, also the this is the thermal shear tensor Xi U lambda, and this delta mu is the difference between the spin chemical potential and the thermal vorticity. And thermal vorticity is just the vorticity associated with the thermal fluid. Okay. So this shows that if you have a thermal vorticity, or if you have a thermal shear, or if you have a finite spin chemical potential, then the spin would be polarized. So this NF is the Fermi-Dirac distribution. So this can be considered as some susceptibility. So it's some kind of susceptibility times some source gives us the polarization vector. Okay. Suppose we have a hypersurface Xi on which both spin and also the particle number are frozen out. Then we can integrate over this hypersurface, because this is something like the emission surface for the finally observed hadrons. So then we can integrate over this surface to obtain the polarization vector P mu as a function of the momentum. So the denominator is nothing but just a particle number. So the total spin divided by the total number gives us the polarization.
Excuse
so
me.
Now, yes.
Yeah, just as a comment, I mean, the Cooper-Frye formula is based, the original Cooper-Frye formula is based on detailed balance, right? Here you don't have anything like detailed balance. Because before you basically just have vorticity, and afterwards you have vorticity and spin.
Why Cooper-Frye is based on detailed balance?
It's based on equilibrium, if you want to call it that, between a fluid and a collection of particles.
I'm not sure this is a detailed balance. So Cooper-Frye formula is just a formula that if you have some quantity in the coordinate space, then this formula just tells you the particle number distribution in momentum space, or similarly for the spin in momentum space. Once you integrate over the emission hypersurface.
But the assumptions, how do you derive the Cooper-Frye formula, right? The assumption is that the assumption is that energy momentum conservation, of course, and also entropy conservation. I mean, it's not entropy, the gradients of entropy are in equilibrium with each other. This is not true here.
But angular momentum is conserved as well.
Yeah, but on one side, you have just angular momentum, and on the other side, you have spin and angular momentum.
Maybe I still
with thermal weights, with thermal weights in it. So I mean, if you, at least in the sort of ideal fluid limit, if you run the Cooper-Frye formula back in time, the particles will make a fluid. Here, I'm not sure. Here, this is not the case. Certainly, it's not the case with the thermal shear tensor, but I think it's also not the case with the just with the vorticity tensor.
Right.
This is just a comment. I'm just saying that I would be careful about in the ideal limit, the Cooper-Frye formula is a statement about detailed balance between a fluid and free streaming particles, if you want. With polarization, this becomes an issue.
Why is it not an issue already with charges?
Like with chemical potentials. Because if you add chemical potential, you will have more positive particles than negative particles, whatever, but it's still think of it this way. In the ideal fluid limit, no, but not just in the ideal fluid limit, even if you if you put in the viscous part of the energy momentum tensor, the Cooper-Frye formula is a sort of a volume element in which you convert a fluid into particles, right? If you go back in that step, you go from particles to a fluid, you get the same fluid. Because the point is that nothing special happens at that point, right? Before you count it as a fluid and afterwards you count it as particles. So for chemical potential, this is not an issue. You'll just have a charge imbalance. But for polarization, you spoil this.
Why? I still, you didn't say why, Giorgio. Like, are you saying because the spin is not a separately conserved quantity?
I believe so, yes.
No, but I mean, the total angular momentum is conserved. So you can still do the detailed balance in the total angular momentum. And then how you break that up into polarization is a different issue. That's pseudo gauge dependent anyway. But I think the angular momentum, the total angular momentum, including the orbital part, should go through the Cooper-Frye.
The point is, I will write down. I just wrote down this. Take the entropy current and differentiate it by the volume element of your freeze-out hypersurface. What I mean about detailed balance is that this thing for the fluid is the same thing as for the free streaming particles.
So maybe we should discuss this towards the end. So, like, thanks for the comment. But
no, of course.
As far as I understand, this is only tangential to what Xu-Guang wants to tell us. So.
Yeah, maybe we can discuss later.
Yeah, definitely. Let's talk about it after.
Fully understood what the comment. Yeah, maybe we can discuss later. Yes. So this formula tells that once we know the spatial distribution of spin chemical potential and the spatial distribution of the velocity gradient, then we could be able to calculate the spin polarization in momentum space. For the spatial distribution of the velocity gradient and also the gradient of temperature, we already have a lot of well-established models like the hydro model or transfer models that can be used to do the calculation. But for the spin chemical potential, so far actually, I don't know whether there is someone trying to calculate the spin chemical potential. So then we want to see under which condition we could be able to know what the spin chemical potential is. So one such condition is the global equilibrium condition. So global equilibrium means that this density operator becomes globally independent of the choice of the hypersurface. So this is so it becomes stationary. And this gives the condition that there is no thermal shear, and also the spin chemical potential is determined by the thermal vorticity. Okay. So under this condition, the spin polarization formula becomes much more simpler. So it becomes this form, and this form simply tells us that if there is a thermal vorticity, then this thermal vorticity polarizes spin, and which other parts can be considered as a susceptibility. Okay. Yeah, but in this formula, we say that spin polarization is completely determined by the property of the fluid vorticity. So the spin polarization itself is not dynamical. But the good thing is that this formula is easy to use because the thermal vorticity is easy to calculate. Then we can see, okay, so with having the thermal vorticity, how is the spin polarization? Yeah, for example, if we want to study the global polarization, then we can calculate thermal vorticity. Then we integrate all the volume of the phase-out hypersurface. Then you can also integrate over all the momentum. So then you can obtain the global polarization. And the theoretical calculation agrees. The theoretical calculation agrees with the experiment data quite well. So namely, what is the interpretation of the global spin polarization works quite well for this case. And for the cascade and omega polarization, so again, the theoretical calculation can fit to the data. So which means the vorticity interpretation for the global spin polarization for those hyperons seems to work quite well. Yeah. So this means the vorticity actually provide a bridge that connects that connect the initial global angular momentum to the final global spin polarization. So then let's try to apply the same formula to study the local spin polarization, namely how the spin polarization is distributed to different azimuthal angle. In this case, there appear a big problem. So this is a calculation from Bagatini and Karpenko from hydrodynamics. What they found is that, so here, with azimuthal angle between 0 and pi half, the spin polarization, the longitudinal spin polarization is actually negative. But the data shows that in this regime, the longitudinal polarization is actually positive. So similarly, if we look at the transverse polarization, the transverse polarization as function for phi decreases with increasing azimuthal angle from the data, but from the calculation, it increases. So there is a sign difference between the data and the theoretical calculation based on the vorticity picture. So this is a big problem. So to understand why this happens from theoretical side, we need to first understand the vorticity, right? But I think the vorticity is quite well understood. And also we need to study the fade down distribution. That's because the measured, let's say the measured lambda hyperon are not only from the primary hydrogenization. There are a lot of lambda from the decay from heavier particles, and these are not included in those calculations. So this should be taken into account. And also possibly we should go beyond the equilibrium picture. So we should treat spin as independent dynamic degree freedom. So there could be different framework to do this. One is the hydrodynamic framework, then the kinetic framework. Also, there are some other possibilities that have been studied. One is that we can choose different spin chemical potential. I mean, do not to slave spin chemical potential to thermal vorticity, and also to see the contribution from other terms. Okay, so for the fade down contribution, yeah, I just tell the conclusion is that the fade down contribution, the fade down decays give a big contribution to the total number of lambda. Actually, about 80% of the lambdas are from the decay of the fade down. But the fade down contribution from the spin polarization is actually very small. It's about 10%. That's because the fade down contribution from different particles will have either positive sign or negative sign. If you add them together, they cancel each other. So which means the fade down contribution does not solve the sign problem. Okay, so there could be other possibility. As I said, one possibility is that we do not enslave the spin chemical potential to the thermal vorticity, which means we can relax the global equilibrium condition. The global equilibrium conditions are two. First one is that the thermal shear tensor is 0. Another one is that the spin chemical potential is equal to the thermal vorticity. So let's keep the first one, but change the second one. So let's see if the spin chemical potential is given by not the thermal vorticity, but this vorticity, sometimes called the temperature vorticity. And in this case, indeed, all the data can be fitted by the calculus. Here, the black line is the temperature vorticity, blue line is the kinematic vorticity, the red line is the thermal vorticity. You see that with the temperature vorticity, the theoretical calculation fits to the data for the longitudinal polarization and actually also for the transfer polarization. So another way you could try, okay, so let's turn on the thermal shear contribution. So that's first studied by two groups. The results are very interesting. So with the which means in this case, the spin chemical potential is still given by the thermal vorticity, but we do not impose the vanishing thermal shear condition. Namely, we let the thermal shear to be non-zero. So there would be the contribution from the thermal shear, and under some assumption, the measure calculation can also be tuned to fit to the data. Okay. Yeah. Yeah, but of course, those I think those studies are not that satisfactory, because they somehow take, I think, big assumptions. So more reliable calculations should be given in the following way: that we have both shear contribution, vorticity contribution, and should also the spin chemical potential contribution. But to know how the spin chemical potential contribute to the polarization, we need a dynamical theory to calculate how the spin chemical potential evolves from the beginning to the phase out moment. Okay, so which means we need a theory, dynamical theory for the spin chemical potential. Such a dynamical theory could be a kinetic theory or any other dynamical theory, but we want to develop a hydrodynamic theory. That is because the hydrodynamics is a kind of a standard tools to describe the Planck evolution of the Gluon plasma in hyperon condition. So quite useful. Thus, if we can encode spin into hydrodynamics, could be also we impact that it could be also quite useful to study the spin polarization. For the spin hydrodynamics, so in this framework, the spin is considered as a hydrodynamic variable. In fact, in the non-relativistic system, a similar framework has been considered in both spintronics and also in some special situation in which they need some special theory to describe the fluid, like our blood or some fluid with microstructure. So here, the macropolar means the fluid cell can have internal rotation, so that there's a polar direction. So this special fluid need a special fluid mechanics that is called macropolar fluid. Yeah, I think this is a big, maybe already a big branch of fluid mechanics, because there are already several books on this topic. So what we want to have, I think, is similar. So we want to have the hydrodynamic framework in which spin is treated as an independent dynamic variable. So, but for hydrodynamics, we know that the hydrodynamics is a low energy effective theory for the conserved quantities. Yeah, so only the conserved quantities are dynamic variables in the hydrodynamics, and those variables does not relax if the system is homogeneous, because they are conserved. Thus, we can study how when there is a small inhomogeneity, then how those variables evolve in time. That's the hydrodynamics. Thus, hydrodynamics is constructed by gradient expansion. And for our case, the usual hydro modes are the energy density, momentum density, ion density, and so on. For spin, if spin is conserved, then it's quite straightforward to write down the conservation equation for the spin. Then do the gradient expansion to the charge current, energy momentum tensor, and the spin current. We can construct the spin hydrodynamics. And usually the leading order terms are corresponding to the ideal hydrodynamics. So this was first done by Volokovsky and his collaborators. So they developed the ideal spin hydrodynamics. But we know that in general, spin is not conserved. Only the total angular momentum is conserved. So which means spin in general is not a strict hydrodynamic variable. Yeah, so the spin current is not conserved. Its divergence is equal to the anti-symmetric part of the stress tensor. And due to this non-conservation of spin, the spin angular momentum can be transferred to the orbital angular momentum, and also the orbital angular momentum can be transferred to the spin angular momentum. And this conversion between spin and the orbital angular momentum is in general dissipative. So which means if we do not, I mean, in general, we should consider a dissipative spin hydrodynamics. Yeah, so in the following, I want to focus on our recent work about the development of dissipative spin hydrodynamics in collaboration with Masaru Hongo and also one of the organizers, Matthias, and also Misha, Stefanov, and Hong Yi. That appeared last year. Yeah, because spin is not conserved, it's not a hydrodynamic variable. So, which means we should, if we want a hydrodynamic theory, we need to extend this hydrodynamic theory to somewhere to include spin degree freedom. This is possible when there is a clear serial separation between the spin relaxation rate and other relaxation rate other faster modes. So if this is possible, and when the spin relaxation rate is much smaller than the relaxation rate of all the other faster modes, we could have a theory in which the strict hydro modes plus the spin modes are included. So this is a kind of spin plus for spin, hydro plus for spin. Sorry. Okay, so then this is our working assumption. So the spin relaxation rate is much smaller than the relaxation rates of other modes, so that we could have a well-defined hydro plus regime. That's the spin hydrodynamics. Later, we will discuss in which case this can be realized. Another problem for the construction of spin hydrodynamics is that spin current, the definition of spin current is ambiguous. That is because the total angular momentum is conserved. So you could put how much of the total angular momentum into the spin part and into orbital part is kind of your choice. And this choice, this freedom of choice is sometimes called the pseudo gauge freedom. So namely, you can do a transformation in this way to change the definition of your spin current and stress current. This pseudo gauge transformation is not a true gauge transformation, because this pseudo gauge transformation actually connects different physical observables. So this, which means this pseudo gauge transformation can change observable. So it's not a true gauge transformation. Yeah, because of this, it's not a true gauge transformation. So if you want to formulate your spin hydrodynamics, the first thing is to choose a pseudo gauge. That is, you first need to fix your definition for your stress tensor and spin tensor to some degree. Okay. Yeah, and there are some works. Recently, there are some works that develop the spin hydrodynamics by using different pseudo gauges. So in the following, we focus on the following way to fix the pseudo gauge. That is, we couple the spin to a torsion. Okay, so which means we will define the spin current as the gauge current for the gauge Poincare symmetry. So this is used in our work and also used in the work by Umut a year ago. So which means we can gauge the Poincare symmetry, and in that case the fear band is the gauge field for the translation, and the spin, this omega mu AB is the spin connection. The spin connection is the gauge field for the Lorentz transformation. And finally, if you gauge the Poincare symmetry, you will end up with a field theory formulated in a Einstein-Cardan spacetime. Okay, and the current, the gauge current for the fear band and for the spin connection are just the energy stress tensor and the spin current. And in this way, for example, for QCD, you found that the spin current is just the canonical spin current. And once you define the theory in the Einstein-Cardan spacetime, the conservation laws becomes what Takahashi identities for the diffeomorphism and local Lorentz varies here. Okay, so with this equation motion, we can construct the spin hydrodynamics. Then we need to identify what would be the hydro variable. In our case, we have the energy density, momentum. So here the velocity, and also if we have a U1 charge, then we have a charge density N. then the spin density sigma AB. Yeah. Okay. Yeah, with those hydro variables, we decompose the stress tensor and the spin tensor using the hydro or quasi-hydro variables, and then require the local thermodynamics, first law and second law of thermodynamics, and also do the gradient expansion. So in this case, we account the spin, chemical potential, spin density, and also spin connection as the first order quantities in gradient. In principle, you can also do the power counting another way. For example, you can consider the spin, chemical potential, or spin connection as a zeroth order quantity. Then you will find another theory. But that would be also interesting because that means you have a hydrodynamic theory about a globally rotating equilibrium state. But in our case, we use this power counting scheme. Okay, then the second law.
Sorry, Xu-Guang, can I ask a question about your previous comment that you can consider the spin chemical potential and the spin density as zeroth order quantity? So but that means essentially that in the hydrostatic limit you would have some global equilibrium with a non-trivial spin polarization, right?
Right.
But so that means and also for the vorticity, for example, I mean that how would that be consistent with so that would be acausal, I think, right? So you have some kind of a rotating fluid,
right?
Even if you assume
okay, so the system must be finite. If you have
the system must be finite, right? But if the system is finite, then you have to. There are more degrees of freedom that comes from the boundaries. I mean, not essentially not degrees of freedom, but the boundary conditions. So you have to impose some certain boundary conditions.
That's
so that's because like all this. So for example, like the first law that you're using here and all the basic definitions depend on the fact that this is an extensive system, I think. I mean, what I'm saying is that what you are doing seems more right, better than just assuming that it's zeroth order. So I don't really know honestly how to do it in the second.
What we are doing is simpler.
Right.
And what I said that we have a globally rotating equilibrium, that's harder certainly, and also there would be some issue like how the boundary condition can influence the mode in the bunk. Right. Maybe another way is to consider rotating frame. Yeah, but for this rigid rotating equilibrium, we can consider the regime near the rotating axis. So that suppose the boundary is far away, so that it will not influence much the physics near the rotating axis. Yeah, I'm not sure, but yes, in principle, in this case, there must be a boundary, and the boundary condition may play some interesting role.
Yeah, I think so too. Yeah, thanks.
Yeah, thanks for the comment.
Just a comment. I think in the appendix of the paper that Xu-Guang cited, there's an example where such a state is realized. At least the equilibrium state is realized.
Right. Yeah. There is a equilibrium state, which is under rigid rotation, and which must be finite. Yeah, that is in our.
Yeah, I know. Well, I mean, so yes, but in that case, I think so. So that should be a finite system, right? So Matthias, you agree that because if it is not finite, it will be causal. Yeah.
Right. Right. Yeah. Okay. So yeah, finally we got this constitutive relations. So there are three viscosities. One is the usual shear viscosity, another is the bulk viscosity, and this is a new viscosity called the rotational viscosity, which appears in the anti-symmetric part of the energy of the tensor. Okay. Then with the equilibrium state, which connects the pressure to the densities, with those equations and also the equation state, the hydrodynamic equations are closed. Okay. Yeah, then we can study how the hydromoles, linear hydromoles evolve, or study the dispersion relation of the hydromoles or quasi-hydromoles in this framework. And this is the result. So we just perturb a static thermal equilibrium and then solve the linear equation for those conditions. And often those dispersion relations. The first one is the usual sound wave. Second one is the longitudinal spin modes. That's the spin modes parallel to the momentum. And this is the shear mode. And finally, there is a transverse spin mode. And then you see that those spin modes are not really the hydro mode. They have a finite realization rate, gamma s. That's it's quite interesting to ask under which condition we could have this spin hydro framework, because it requires that the spin relaxation rate is, although it's not zero at zero momentum, but it should be much smaller than the relaxation rates of other modes. And another thing is that to calculate the spin relaxation rate, if the spin hydrodynamics can apply. Okay, so there's one example that the spin hydrodynamics can be justified. That is if the system contains heavy fermions, heavy direct fermions. Because for heavy direct fermions, the spin orbital coupling is given by this form. You see, if the mass is large enough, see if the mass is much larger than any other scale of the system, then this is a small quantity. And if the spin orbital coupling is small, then the conversion between spin and orbital angular momentum will be summarized, and we have a passively conserved spin, and thus we have the spin hydrodynamics. Then let's consider QCD. So in the heavy quark limit, the QCD becomes non-relativistic and given by this way. The leading order is just the mass, and the subleading order, also the subleading order. And this is the spin orbital coupling. So this is for the heavy quarks, and there could also be the gluon part. That's the usual gluon Lagrangian. Yeah, and in this case, the equation motion for spin density is given by this form. So here, this JA0 is nothing but the sigma AB that we have in the relativistic case, but we use a different notation because now we are considering a non-relativistic theory. So, and this J is the sigma mu rho sigma in the relativistic case. Okay, and yes. This zeta A. Yes.
Sorry, what is B? Is the mag?
Oh yeah, B is the color magnetic field here.
The chiral magnet. Okay, I see. So that's
color,
the
chromomagnetic field.
The chromomagnetic fields. Yeah. So because you want to. So where is the vorticity entering in this picture?
No, there's no vorticity. This is just the Lagrangian. I mean, if you have a gluon, this is still dynamic. This B is not external. It's still dynamic. Because you have a kinetic, and also you have this gluon Lagrangian. This B is dynamic. This chromomagnetic field is not a external field.
I see. Okay. So, but this is kind of this is like a model. Well, this is the heavy quark limit of QCD. I see, but like if you want to directly apply it to the quark-gluon plasma, there the argument was that this essentially you get the polarization due to the spin orbit coupling, so the coupling between the spin and the vorticity. So here the role played by the role of vorticity is here played by the chromomagnetic fields in some sense, right?
Yeah, in some sense, yes.
But is that also relevant for QGP, or should I think of this as some model where you can do the computation?
I'm not sure how can we really apply this Lagrangian to QGP. Because if we want to apply this Lagrangian to QGP, we need to couple. We have this coupling, the spin of the coupling, which can be used to polarize the spin of heavy quark. But then we need to really know how the gluon field, is filling the vorticity.
Right.
Now, this maybe can be done. So if we have a collective ocean for gluonic matter, this maybe there's some way to formulate that we have a rotating gluonic matter, then we have this coupling, then this rotating gluonic matter could polarize the spin of heavy.
Yeah, so I mean, like, all I'm saying is that if this is the case, if this can be used as in some limit as a model for QGP, then in all the original considerations of spin hydrodynamics, which was mostly based on vorticity, is kind of missing also this element, right? So the chromomagnetic field due to gluon. So that was never considered in the hydro models. So if you can also introduce this as a hydrodynamic degree of freedom somehow, then maybe it will change the this local polarization picture and all that story.
Maybe this in the hydrodynamic picture, the gluon can contribute to the stress tensor. Thus, they can contribute to the vorticity, and then this term should corresponding to the right here. Right. This term should just come if in the spin hydro, this term should be just corresponding to the source for the spin non-conservation.
So I hate to rush everybody, but maybe since the time is progressing, maybe Xu-Guang, you can make your point, your final point, and then come to your summary.
Right.
Thank you.
Okay, so we have this non-relativistic limit for QCD, and then we can derive two couple-like formulas. So one relates the spin relaxation rate of a heavy quark to the source polarizer. Here the source is nothing but this spin violation term, which is nothing but the antisymmetric part of the energy tensor. So another formula relates the inverse of the spin relaxation rate to the spin correlator. Okay, so we have two different ways to calculate the spin relaxation rate. So either by calculate the source correlator or the spin correlator. So this was done recently. This paper is also collaborating with Matthias, Misha. Okay. So for the calculation of the spin correlator, which is very much like the calculation of a shear viscosity. So the correlator is given by this diagram, but in the zero frequency limit, this diagram gives the pinching singularity. So to kill the CP singularity, we need to do the resummation of the vortex, which is achieved by solving the Bessel equation. Once these are done, once those calculations are done, we can obtain the spin relaxation rate by using that formula, and this is the result for the spin relaxation rate of heavy quark at leading order. Okay, so comparing to the usual result, you can see that there is a T over F squared separation. And because we know that those procedure is equivalent to solving a linearized Boltzmann equation, so we explicitly checked that this is indeed can also be obtained by solving the Boltzmann equation. Now, those calculations are actually quite tedious, but there is a very interesting and much simpler calculation by considering the source-source correlator in the quasi or in the spin hydro regime. So in that case, what we need is only to calculate the one diagram. And this diagram, in this diagram, there's no pinching similarity, which means just calculate this two-loop diagram. And we don't need to do the resummation. Technically, this is because once we have this gluon line, the momentum flowing on this gluon line just cancels the pinching pole from these two fermion lines. So finally, the result is the same, but the calculation is much smaller, simpler. Okay, so this is the perturbative result in the perturbative region at the leading log order. Yeah, it could be interesting to considering not this weakly coupled limit, but the strongly coupled limit from holography. So yeah, with this, let me summarize. So we say that the spin polarization hyperons observed at hyperons collision. It seems that we need a dynamic theory for spin to have a full understanding of the data. So for that, we have developed dissipative spin hydrodynamics, and which with the spin quark formula could be possibly used to study the spin polarization of hyperons in the hyperon conditions. And in future, there could be many other possible directions to go. For example, to develop a stable and causal spin hydro, to calculate additional viscosity or other transport coefficient in the spin hydrodynamics by using holographic method, and also to construct the spin hydro with other ingredient like magnetic field anomaly, or if there is a globally rotating equilibrium state. Also, to understand the spin hydrodynamics from theory, and also I think it's quite important. But importantly, that we should develop an America code to study the Lambda polarization application. So okay, thank you. Yeah, I'm sorry I took too much time.
That's fine. Thank you so much, Xu-Guang. We started 5 minutes late, so and you got a lot of questions, which is great. So thanks to you and thanks to the audience for the questions. Let's take maybe 2 more questions, just so that we have a time limit on the talk. I mean, we can still keep talking, but we don't want to exhaust everyone, especially our speaker. But yeah, just other questions.
Matthias, can I ask?
Of course.
Xu-Guang, thanks a lot for the nice talk. My question is about the last part of your talk. Oh yeah. In the part that you spoke about the heavy quark model, I didn't understand why the first contribution to the spin relaxation rate came from the loop effects. Why not any 3-level effect? Yeah, exactly here, exactly.
Oh, no, this is, yeah, okay, so this is the correlation function. Because from this, you see the spin relaxation rate is given by some limit of the correlation function, which means we need to calculate the correlation function. Yeah, this is nothing but the one loop contribution to the correlation function.
So you mean the correlation function in the hydrodynamic limit vanishes in this.
Yeah, the logic.
I mean that.
Yeah, the logic is that from the hydrodynamics, we found that there's a relation between the transport coefficient and the retarded Green's function. And because the hydrodynamics is a universal theory, so we expect that if you have a field theory, then you have the retarded Green's function, and then in the spin hydro regime, that retarded Green's function must agree with the hydrodynamic retarded Green's function. That gives us the Cooper formula, and this Cooper formula relates the spin relaxation rate to certain correlation functions. And in order to calculate those correlation functions, this is the leading diagrams. Because, for example, this J contains Poisson dagger, some operator aside. This JB also contains Poisson dagger, some operator aside. Thus, this leading diagram is a one-loop diagram.
Okay,
similar
okay. So
this case.
there is no any tree level. I mean, if you use psi dagger psi in the left side, psi dagger psi in the right side, it is not possible to construct a diagram without loop.
No, I don't think it's possible.
I see.
Yeah. That's the diagram.
Thanks.
I see that Umod has a question.
Yeah, sorry for asking too many questions, but it's very interesting. So thank you very much for the talk. Yeah, so what I just was wondering about this pseudo gauge issue. So like this computation you did in a particular gauge, I think, and I was wondering if the correlation function depends on, for example, the pseudo gauge you choose.
I think so.
And but can you find an argument that the scaling would be independent? Because
no, I don't think the scaling would be independent. I think that it depends on the pseudo gauge.
I see. So it's a bit okay. So but then there is this ambiguity still, right?
Right. I think so.
Okay.
Yeah. This is for specific pseudo gauge. For example, if you consider the canonical spin, it relaxes at this rate. But if you consider another spin, it could relax at a different rate.
I see.
That's my, yeah.
So like the separation of scales that you assumed in the beginning is that's gauge dependent, the pseudo gauge dependent assumption in some sense.
Yeah, assumptions, yes. If there is a pseudo gauge which violates that scale separation, then which means under that pseudo gauge we cannot formulate a reliable spin hydro.
Yeah, this is very confusing, right? Because like this is still like polarization is something that is observed. This is an observable. So that's
right.
And I would expect that the spin relaxation rate. I mean, the global polarization may be something else. The 1-point functions can be dependent, but like these correlation functions, these 2-point functions, and especially these transport coefficients, I would expect them to be independent of the formulation. But you're saying essentially this is not just a usual gauge dependence, but it's like, you know, the quantity that you're computing also depends on the gauge you choose.
Yeah, that's why I think so is because from the formula you see this quantity is determined by the correlation function of the those quantities, and those quantities are depending on pseudo gauge. Yeah, because this is the eigenmoment tensor, this is the spin intensity. You can choose different gauge. You change the definition of this spin intensity operator, and also the stress tensor operator. So which would lead to I think it would lead to different results for the spin relaxation rate. At least I cannot say that it really should be independent of pseudo gauge. If those operators are depending on certain things.
Yeah, that I would argue that's still an open question in the framework. So, and I think I agree that it's puzzling. Maybe we take the diffuse question as the last question, and then we can stop the recording and talk a little more for people who are interested. But just to Defu, you have a question?
Okay, thank you very much, Xu-Guang, for your nice talk.
Yeah, thank you.
Hi. I have a question about the last point. You computed the spin relaxation rate by two different approaches. Yeah, the Cooper formula, the first one, you included this the net resolution, and the next second approach, you simply calculate the two loop, and you gave the same result.
Right.
So I'm wondering, yeah, that's very interesting. I'm wondering, is there any physics maximum behind or physics interpretation for this?
Yeah, for the resummation, right? For the resummation case, it's a kind of standard calculation for any transport.
Yeah, I know that this. I just try to understand why they gave two different approach. This include a lot of ladder resummations. The second one is just the two loop calculations. They gave the same results.
Right. Yeah.
Exactly the same result. Yeah.
Yes, this is a possible because spin is not really conserved quantity. So which means it could be calculated by using the density operator, and also because it's not conserved, so it has a source. It could also be calculated by the source correlator. So if we see, for example, a transport coefficient like the shear viscosity, we do not have. There is no source for that, so we do not have this formula, and we have to do the resummation. Yeah, so yeah, that's a very special property for the non-conservation
spin.
It's only because that the spin is not conserved. Yeah.
Okay.
Yeah, for example, if spin is conserved, this is simply 0 because this conserved density correlator. So right. So yeah.
Okay, great. So thanks for the questions, and again, thanks for the talk. So let's close for today. Thank you again.